In this video, we're going to solve some tank problems. These are problems in which we've got a tank that's full, or at least partially full, of some fluid, and we are trying to empty the tank by pumping the fluid out of some spout. So here's our first example problem. This is probably the easiest problem that you'll see in our class anyway. It's particularly easy because of the geometry of this tank. Now this is a little bit too easy for a test question or a quiz question, so just keep that in mind. This is just a problem to get started and talk about the idea. So, excuse me. Here's our problem statement. So our tank is nearly full. It has water almost all the way to the top, and the water level is 1 foot from the top of the tank. So we've got water until we're right here in the tank, and that's 1 foot away from the top. It says if water has a weight of 62.4 pounds per cubic foot, notice that's units of force per units of volume, how much work is required to pump the water to the top of the tank? Well, let's think about it. If we've got a spout that's right here, so it's coming out just straight from the top of the tank, work is force times distance. We know that, right? The question always becomes in this section, do I need calculus to empty this tank or not? Well, you could say, well, if I know that water weighs 62.4 pounds per cubic foot, I'll just take this and I'll multiply by the density, multiply by the volume of water in the tank, and then I will just multiply by the distance that whole thing moves through. Well, the problem is, not all of the water moves the same distance. If we are pumping the water to the top of the tank so that it's coming out of this little spout, and we're not worried about pumping it back and forth, we're just trying to get it up to that water level, or to that top level. The water at the bottom of the tank is going to have to move a farther distance than the water at the top of the tank. So with all of that in mind, since the distance varies from the bottom of the tank to the top of the tank, we're going to need calculus to find the work. So we're going to find the work done on one piece. So that means I need the force acting on that piece times the distance the piece moves through. That's what that I means. It's the work done on the ith piece. And notice I've got density. Whenever you're working a tank problem, they're always going to have to give you density of some kind. This is a weight density. It's the weight of water per cubic foot. So it's giving me force per unit volume. And that's going to be a characteristic of the fluid. So that can either be a weight density like this, or a true density, mass per unit volume, times acceleration due to gravity. But either one of these will work. So we're going to have force per unit volume. That's a characteristic of the fluid, and it's going to be posed to you either this way as a weight density or this way as a traditional density times gravity. And if I take that force per unit volume and I multiply it by volume of a slice and the distance that slice moves through, then the volumes are going to cancel, and we're just going to have force times distance, and that's going to give me the work for that slice. Now I want to slice this in such a way that the entire slice has the same force acting on it, and it moves through the same distance. Well, it makes sense then, in this case, I'm not going to slice it this way, because the water at the bottom moves a different distance than the water at the top. I need to slice it so that the entire slice is at the same distance from the top. So we're going to slice parallel to the top for these problems. so that our entire slice is at the same distance from the top. So that's my slice. And now I just need to find the volume of that slice and the distance that slice moves through, and I'm going to multiply it by the force per unit volume, which was given to us. And then that's going to give me the work done to move that slice to the top. So we slice parallel to the top of the tank. We also need to write down our formula. So this is going to be force per unit volume times volume times distance every time. And now we just find each of the pieces. Force per unit volume was given to us. That was 62.4 pounds. It's units of force over cubic feet, which makes sense. And I want the volume of that slice. Now, that slice has a constant area, so that makes this really nice, a very nice problem. Most of the problems we work in this section, like a test type question, aren't going to have a constant area. So this is just a starter problem. Let's think about the volume of that slice. The volume is this dimension times this dimension times this dimension. And this is always 10, according to this. If that's 10, this is 10, if it's a rectangle. And if this is 15, then that's 15. So this is 15 feet by 10 feet, or 150 square feet, times delta y feet. So it's 150 delta y cubic feet. Not too bad. So I wrote my formula down, and then you find the volume of your slice. So we're going to have to rely on those skills that we learned in previous sections. When we looked at volumes of solids with known cross-sections, we had to find the area times the thickness. In this case, we're always going to find the area times the thickness as well, but because we're slicing parallel to the top, the thickness is almost always going to be delta y. In this case, our area was just 15 times 10, which was 150 square feet, times delta y feet gave us 150 delta y feet cubed. So these units reduce. Now I just have this times this times this, pounds. That's how many pounds I have in that one piece. Now I have to think about the distance that moves through. Well, the distance is this distance from here to here. Now, how we represent that depends entirely on where we decide y equals 0 is. Now, to make this as simple as possible, I'm going to do what we did last time. Let's put y equals 0 at the top and call this the positive y direction. If that's the positive y direction, the distance from here to here, if y equals 0 is at the top of the tank, not the water level, but the top of the tank, the distance is just y. When we're all the way at the bottom, the distance is going to be 18 feet. When we are 2 feet from the top, the distance is going to be 2 feet. When we're 10 feet from the top, the distance is going to be 10. So in general, it's going to be y feet. And then when we multiply those together, we get 62.4 times 150 times y sub I times delta y, and these are pounds times feet, they're foot-pounds, and that's the amount of work done in moving that one piece. So we found the volume of the ith slice, and we also found the distance the ith slice moves through. And then of course we substitute into the formula. And now we want to find the work integral. The total work is the limit as the number of pieces goes to infinity of the sum as I goes from 1 to n of the work on the ith piece, and this was the work on the ith piece. So total work is the limit as the number of pieces goes to infinity of the sum as I goes from 1 to n of this guy that I just found. And those are foot-pounds. And that's the definition of this integral, 62.4 times 150 times y dy. Careful here. The limits of integration come from those pieces that you're moving. So it's not going to be all the y values shown in this picture. We're going to have to use the y values wherever we have fluid. So given that this is y equals 0, we don't start to have fluid until y equals 1. And then we have fluid in our tank from y equals 1 to y equals 18. So those are our limits of integration. All right, so now we can anti-differentiate. So I have 62.4 times 150. Add 1 to the exponent, divide by the new exponent, plug in 1, plug in 18, and subtract. So I have 62.4 times 75. 18 squared minus 1 squared. Multiply all those together. And this is exactly what I get in my calculator. I know this is not the proper significant figures, but that's what I've got. 1,511,640 foot-pounds of work are required to empty the tank. Alright, so that's a simple example because it has simple geometry. Now most of the problems aren't that simple. Most of the tanks, or most of those volume slices, have variable area. It's not just going to be 150 square feet times some delta y feet most of the time. So let's look at an example that's more advanced, something more like you would see on a test or a quiz. So here's another example. You've got a hemispherical tank. It's full of benzene. Benzene weighs 56 pounds per cubic foot. And we're given the dimensions of the tank. We're told the diameter of the tank is 10 feet, which means its radius is 5 feet. We've got a spout that goes from the top of the tank up 2 feet. And we're told that this is full of benzene, and then we're asked how much work is required to pump the benzene out of the spout. Well, we're going to do the same thing that we did last time. We want to find the work done to move one piece, and that's going to be the force acting on that piece times the distance that piece moves through. Now we have to use calculus to do this because not all of the pieces move through the same distance. These pieces at the top are going to move through a much shorter distance than these pieces at the bottom. Like that slice, if I take a slice at the bottom, it's going to have to move through 7 feet. This piece closer to the top might have to move through 2 or maybe 3 feet, just depending on what piece we're talking about. So calculus is required. So let's slice this thing. We want to slice it so that every slice or every part of the slice is moving through the same distance. So I'm going to draw it this way. I'm going to draw it on my XY coordinate system. Now if I look at it from just the right angle, it's just going to look like a semicircle. My spout goes up here to y equals 7. It's a semicircle with a radius of 5. X goes from -5 to 5. We've got y going from 0 to 5 for the semicircle. For the spout, it goes all the way up to y equals 7. And we want to slice this parallel to the top. So if I slice it this way, I'm going to see something like this. Now that's what it looks like in 2D. In 3D, we're going to see it's actually something very similar to what we did in a previous section. It looks like a disc. And we know how to find the volume of a disc. So this is going to be very familiar, but we've got to use those old skills from before. So work is force times distance, and anytime we do a tank problem, they have to give us the density of the fluid in the tank. They told us benzene weighed this much. this many pounds per cubic foot. So that's force per unit volume. I'm going to multiply that by the volume of my slice and multiply that by the distance the slice moves through. Force per unit volume was given to us. That's nice. We'll just fill that in. Do the easy part first. And volume is just the volume of the slice. And distance, that's the distance from this slice all the way to the top. Well, we know if we're slicing this tank this way, the thickness or width of that slice is delta y. And because it was a hemispherical tank, well, that's just a disc. And we know from when we studied the disc method, the volume of a disc is just the area of a circle times the thickness. So I need the radius now. But careful, I don't want the radius in general. I need radius as a function of y. So let's look at our picture. Now notice I superimposed this coordinate system. You're going to have to choose the coordinate system most of the time. No one tells you where the x-axis is or the y-axis is. But I chose my x and y axis to be here so that the center of my circle would be at the origin, which makes the equation of the circle really easy to write down. So given my choice of origin, the radius is the distance, the radius of my disk is the distance from that y-axis out to that point. So that's a horizontal distance. Radius is x on the right minus x on the left because it's horizontal. X on the right is just x. X on the left is 0. So my radius is x, but I don't want x, I want x in terms of y. According to this, I need this x in terms of y. So I need to find the equation of this circle. Now hopefully you remember that if you have a circle with center at x naught, y naught, and radius r, the equation is x minus x naught squared plus y minus y naught squared equals r squared. Now our x naught and y naught are 0 and 0, so this is just x squared plus y squared. R is 5, so that's 25. So that's the equation of the curve, the whole curve. But I don't want the equation of the whole curve. I want x in terms of y while I'm on this curve. So I need to solve this for x. Subtract y squared from both sides, take the square root. We're looking at the positive x value, so we just need the positive square root. So x in terms of y on this side is the square root of 25 minus y sub I squared. Filled that in as your radius, and that's very convenient. The square root and the squaring function undo each other, and our volume of our slice excuse me, is pi times 25 minus y squared times delta y. And if these units are all in feet, this is square feet times feet. These are going to be cubic feet. Gosh, coughing a lot right now. So I have pi times 25 minus y squared times delta y cubic feet. And those cubic feet reduce, and I just end up with some number of pounds of force. Force per unit volume times volume is going to give me force, which is what I need. Work is force times distance, and the distance I'm moving through, that's a vertical distance. It's the top y value minus the bottom y value. The top y value is 7. The bottom y value is just some general y value, so I'll call it y sub I. And that is also in feet. So, we've got our work now. We found work was force times distance. We split that up into force per unit volume times distance. We filled this in, it was given. We found the volume. That required a little bit of geometry. We had to remember how the disk method worked in order to find the volume of this guy. Then we found the distance that the slice moves through. and then you just multiply those together. Then the total work is the limit as the number of slices goes to infinity, the sum as I goes from 1 to n of the w sub I. So that's going to be an integral. So I've got 56 times pi, and that's 25 minus y squared. That's 7 minus y. Delta y becomes dy in the limit. And we're told that this tank was full of benzene. So for a full tank, my y is going to start at 0 and go to 5. Now I know that we are lifting that whole piece up to the spout at a level of y equals 7. That does not matter. That 7 is taken care of by the distance. The part that we're moving, the fluid that's being moved, exists in my tank from y equals 0 to y equals 5. That defines my limits of integration. Okay, so that's my integral, and we can factor out the 56 pi. If I want to evaluate this, I cannot just take the integral of this and the integral of this and multiply them. That's not legal. Don't do it. You've got to distribute. We do 25 times 7. Excuse me. If I have 7 quarters, that's $1.75, right? Outer times outer is minus 25y. Inner times inner is negative 7y squared. And last times last is positive y cubed. We're integrating with respect to y. So bring the 56 down. Then you have a constant. The antiderivative of a constant is a constant times y. Bring the 25 down. The antiderivative of y to the first, you add 1 to the exponent and divide by the new exponent. Then bring the negative 7 down. Here we add 1 to the exponent and divide by the new exponent. And on the last one, add 1 to the exponent and divide by the new exponent. Plug in 0, plug in 5, and subtract. Okay. So you get 175 times 5 minus this times 5 squared minus 7 over 3 times 5 cubed plus 5 to the 4th over 4. All of this evaluated at 0 is just 0. And I'll use my calculator for the arithmetic. So I'm doing 175 times 5 minus 25 times 25 divided by 2 minus 7 over 3 times 5 cubed plus 5 to the 4th over 4. Don't forget to multiply by your 56 pi. And I'm going to get a decimal approximation. So it looks like that's approximately 23,916.7 times pi. And our units were pounds times feet, so these are foot-pounds. Foot-pounds of work, or if you prefer to have the decimal approximation including the pi, that's 75,136.42 foot-pounds. Now, those are not the proper significant figures, but that's what the value of that integral is. Okay, so let's go over the method for these one more time. Oops, that's not the right one. We sketch this. And then we have to decide if calculus applies, and with tank problems it usually does. And then you want to find the work on one piece. Work is always going to be defined by this formula for tank problems. You need force per unit volume. They're either going to give you density, which is mass per unit volume, and you have to multiply by acceleration due to gravity. Or if you're in pounds and feet, you're in English units, they're going to give you a weight density, force per unit volume immediately. Then you need to find the volume of a slice and the distance the slice moves through. That's not the volume of the entire tank. Be careful about that. this slice moves through a different distance than this slice does. And this slice moves through an even shorter distance. So we need to keep track of the volume of that slice and the distance the slice moves through. So for a particular slice, you find the volume. You're always going to slice parallel to the top. And when you slice parallel to the top, you're going to see a common shape. Like this time we had a disk. So the volume of a disk is just pi r squared times delta y. You find the radius in terms of y in much the same way that you did in the section on the disk method. You write that down. You fill that radius in, you square it, and your volume is this, and you fill that in. And then you think about the distance the slice moves through. The distance always includes the distance all the way to the spout. The distance does not depend on where the fluid is in the tank. The limits of the integration, those depend on where the fluid is. The distance is literally the distance this slice moves through. So it moves from here to here. So we have 7 minus y this time. Then that's enough to set up your integral. But remember, you only integrate where you have fluid in your tank. If we are trying to empty the entire tank of benzene and it's full from y equals 0 to y equals 5, we integrate from 0 to 5. And then you just use traditional integration methods and the fundamental theorem to evaluate your integral. Okay, so we're going to do one last problem. One last problem like this. So this is another tank problem. We want the work required to pump half the fluid out of the spout, and this is our tank. The fluid at the bottom of the tank is going to move a longer distance from the fluid at the top. And if we're pumping half of the fluid out of the tank, that means we're moving the top half. We're not going to move the bottom half. So keep that in mind. When you see half of the fluid, you're going to move the top half of the fluid out of the tank. Okay, so with this problem, we know we need calculus. So the first thing we're going to do is slice parallel to the top. Now this is a little bit hard to draw, but notice that that top part of our tank is a rectangle. That means all of our slices are going to be rectangles too. So our slice has an edge like that and an edge like this. And there's actually another, looks like a trapezoid on this end, over here on that end. So that's our slice. If the top is a rectangle, your slice is going to be a rectangle. So we slice parallel to the top. Then you're going to write down your work formula. Work is force times distance, which is force per unit volume times the volume of the slice times the distance the slice moves through and then we're going to fill in these pieces. Now, they told us our density was 900 kilograms per meter cubed. As soon as I see the kilograms and meters, I know that that is a mass per unit volume. So to get force, I'm going to have to take mass per unit volume, that's our density, and multiply by acceleration due to gravity. And we're still multiplying by the volume of the slice and the distance the slice moves through. Okay, so they gave us mass per unit volume is 900 kilograms per meter cubed. Acceleration due to gravity is 9.81 meters per second squared. And the volume of our slice, well, it's a rectangular slab, so now we need to find the volume of the slice of that slab. Now, what I always like to do with these problems when I'm trying to find the volume of something, notice that the slices toward the top are larger. They have larger surface area than the slices toward the bottom. It's because of this trapezoid here. this side length is shorter. It's only 4 meters long at the bottom, but it's 8 meters long at the top. So this dimension is changing from slice to slice. Excuse me. Now I want to think also about, so that's the dimension that's changing. What is staying the same? Well, if I decide that my y-axis is oriented the way it normally is, up and down, that dimension is delta y, and this is going to be 16 for all of the slices. So our volume is length times width times height. The length is 16 meters. The width is unknown. We're going to find that because it changes. The width is 4 meters at the bottom, 8 meters at the top, and it's something different in between. And the height of the slice is delta y every time. So now I need this width, but I need this width as a function of y. I have to be very careful about finding that width as a function of y. So one way that we can do this is, like, we're going to imagine, here's our tank, we're looking at it. We're going to walk around the tank so that we're looking at this side. So we're looking at that trapezoid. So this is our scratch work to find the volume, to find the width of that side. So that's the trapezoidal side that I see right here. Now you can put the origin anywhere as long as the y-axis is vertical because of that delta y that we already chose. Anytime I have a shape that's symmetric like this, it's the same shape on the left as it is on the right. I know my picture doesn't look like that, but it's close enough, right? Anytime I have that symmetry, I tend to put the y-axis through the middle and the x-axis, and the origin at the very center and the bottom of my side. Now we know that this is 4 units long over here, so this is x between -2 and 2 because we're splitting that 4. 2 on this side, 2 on that side. That's 8 units long, so that means that that's x equals 4, and that's y equals 4. And we're shown in our picture that the top of that, the 8 meter long part, that's 5 meters from the bottom. And then our spout is up 3 meters from that at 8. So the width looks like this. The question is, what is that width? Well, notice the distance from there to there is just x. That's x sub I minus, or x on the right minus x on the left. And because of symmetry, this is also x. So the width of that side is this x plus the exact same distance over here, that x. So you're going to get 2 times x sub I. But we need 2 times x sub I on this line as a function of y. Well, that's actually pretty easy. I've got 2 points on the line. I know this point and I know this point. And with those 2 points, I can find the equation of the line. And then once I have the equation of the line, I can solve for x in terms of y or y in terms of x, whichever one I need. So I'm going to focus in on finding the equation of this line now. Y equals mx plus b. We're going to use rise over run. So we start here, we go up 5 and over 2. So our slope is 5 over 2, and then we're multiplying that by x. And when x equals 2, y equals 0. So if x is 2, I'm going to get 5 here. I'm going to have 5 plus a constant equals 0, so I'm going to have a minus 5 there. So you can find the equation of the line any way you want, but I usually just use rise over run, and then just set x equal to 2 and y equal to 0, and use that to solve for b. Now that's the equation of this line. That's y in terms of x. But if I want the width, which is 2x, I need x in terms of y. So I'm going to take this equation and I'm going to solve it for y, or excuse me, solve it for x. So I will add 5 to both sides. and then multiply both sides by 2 over 5 to get rid of the 5 over 2. So my x is 2 over 5 times y sub I plus 5. If you want, you can distribute. You don't have to, though. And distribute the 2 as well. So we're going to get 4 over 5 times y sub I. And this 2 over 5 times 5 is just going to be a 2. 2 times 2 is 4. Okay. So that's the width. What were we doing again? Oh yeah, we're finding the volume. Volume is 16 times width times delta y, and this is our width. So volume, not really leaving myself a lot of room for distance, is 16 times the width times the height of that piece that we just found. Then we have 16 times the delta y, and that's meters times meters times meters is meters cubed. So the meters cubed reduce here, and I've got kilogram meter per second squared. That's a Newton. It's units of force. So all these guys, when I multiply them together, that's giving me that, and that is giving me a force. So now I just need to think about the distance this slice moves through. The distance is that distance in the picture. I've got y at the top minus y at the bottom, so that's going to be 8 minus y sub I. Also in meters. So newtons times meters, that's going to be joules. So I have 900 times 9.81 times 16 times the quantity 4 over 5 times y sub I plus 4 times 8 minus y sub I. And I think I took care of everything except for the delta y. And these are joules. All right. So we sliced parallel to the top. We wrote down our formula for work. We found the volume. That was our next step. Find the volume of the ith slice. When you do, whatever the geometry is of that top piece that you see, that rectangle, that's going to be the area of your slice. So our slice happened to be a rectangular slab. We got this. And then we just needed to find all of that in terms of y. Now to do that, I had to look at my tank and think about what was staying the same and what was varying. The 16 was staying the same, the delta y was staying the same, but this width of the side was varying from slice to slice. So I had to say, okay, if that's varying, I need that as a formula. I need width in terms of y. So I went and I imagined I'm walking around my little tank and I'm coming over to this side and I'm looking at it from the front. And this is what I see. So I look at this picture, I see the width is going to be, that's x and that's x, so the width is 2x. So I find 2x in terms of y by finding the equation of this line and solving it for x as a function of y. Once I know what x is in terms of y, I sub that in and I get width in terms of y. Finally, we've got length times width times height for volume. Then I just say, okay, well given that, this is my distance using the same picture. It's vertical. It's top y value minus bottom y value, 8 minus y, and we're done with that part. So we found the volume, and then after we found the volume, we found the distance. Okay, that's step 4. Step 5 is to write the work integral. So work is the limit as n goes to infinity of the sum as I goes from 1 to n of the w sub I that we just found. So that's 900 times 9.81 times 16 times 4 over 5 times y plus 4. That's an 8 minus y. Delta y becomes dy in the limit. And we integrate wherever we have fluid. Let's see what it said. It said the tank is full of fluid. Okay. Find the work required to pump half of the fluid out of the spout. Well, if we're pumping half of the fluid out of the spout, that means we're not taking all of it. We're just taking the top half. Since the fluid exists from y equals 0 to y equals 5, and we're taking the top half only, We're going to integrate from half of 5, which is 2.5, to 5. So first thing I'll do is I'll take out my constants. I've got two binomials, so I'm going to distribute. First times first. That is 32 over 5 times y. Outer times outer is that. Oops, it's minus. Inner times inner is that. Last times last is minus 4y. Oops, I'm so sorry, guys. There it is. First times first, outer times outer, inner times inner, and last times last. We're here. And now we can anti-differentiate just using our basic rules. So bring your constant down, add 1 to the exponent, divide by the new exponent. Bring your constant down. Add 1 to the exponent, divide by the new exponent. The antiderivative of a constant is your constant times the variable of integration. Bring the constant down, add 1 to the exponent, divide by the new exponent. Plug in 2.5, plug in 5, and subtract. That's going to be your answer. Half of 32 is 16. So I'm going to have 16 over 5 times 5 squared minus 4 over 15 times 5 cubed plus 32 times 5 minus 2 times 5 squared. All of that minus the same constants. Evaluate all of this now at 2.5. All right, now I'm not going to take the time to put that in my calculator and simplify, but that is the amount of work required to empty this tank. The key is the approach. Slice parallel to the top. The geometry of the top tells you the geometry of the slice. Work for our tank problems is always this: force per unit volume times distance. Now if you're in SI units like we were this time, you've got to split it into mass per unit volume, which is density, times acceleration due to gravity. Those are constants, you fill those in, and then you find the volume of the slice and the distance the slice moves through. Volume might be a little tricky. Think about which dimensions are staying the same and which ones are changing. Write those all in terms of y. Then look at that slice and think about how far it moves. Once you have w sub I, add them up, take the limit as the number of slices goes to infinity. That defines an integral. Make sure you distribute so that you can use your anti-differentiation rules. Otherwise, the antiderivative of this times the antiderivative of this, that's not going to give you the correct antiderivative. So you've got to distribute first, you get this, and then just use the fundamental theorem of calculus to finish it. And this is not the final form of the answer. I'm just choosing not to show you what that answer is. You can use a calculator for that. Thanks, guys.